Good morning. My name is Steve Minnie, and I'm the Senior Director of Applications for the AFM, and I'd like to welcome you to the Bruker AFM webinar series. This is titled Nanoscale Thermal Analysis Quantitative Nanoscale Property Mapping with Automated Transition Temperature Microscopy, presented by Thomas Mueller. Before I introduce Thomas, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar, and if you have a question, please type it into the questions dialog box on your screen. We'll accumulate these questions through the presentation, group them, and then answer them at the end of the prepared remarks. Quite often, we'll have more questions than we can answer in the session. In those cases, we'll be sure to follow up with answers via email afterwards. Also, if you'd like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within 1 week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you'll be receiving an email with this link. Finally, when you exit the webinar software, you'll be asked to take a brief survey. We'd very much appreciate it if you take the time to complete this, as it helps us pick the topics that are most important to you and generally make this series better. So let's get started, and let me introduce our presenter, Thomas Mueller. Thomas received his PhD in 2000 from Yale University on developing novel linear and nonlinear spectroscopic probes of molecular structure. He followed this thesis work with postdoctoral research at Columbia University, focusing on scanning probe microscopy as a tool for interrogating self-assembly and chemical reaction specificity. At Bruker, Thomas has served in several marketing and applications roles and is currently managing product lines and investigating extensions of SPM towards chemical identification and quantitative property measurement. Thomas has over 10 years of AFM experience and is the author of 40 publications, reviews, and applications notes. So now let me turn it over to Thomas for a talk titled Nanoscale Thermal Analysis Quantitative Nanoscale Property Mapping with Automated Transition Temperature Microscopy.
Thank you very much, Steve, and thank you, everybody. Good morning, good afternoon. Thanks for joining us for this webinar about nanoscale thermal analysis. As Steve said already, I'll focus today in particular on the new capability that we're introducing now, automated transition temperature microscopy. So in this presentation today, first I'll give a very brief introduction about the role AFMs can play in polymer characterization and where nanoscale thermal analysis can come in. Then secondly, I give a deeper dive into our nanoscale thermal analysis, how it works, a number of application examples showing its benefits and the breadth of the applicability. And in the third part of the presentation, I'll really then focus on the new capability, the transition temperature microscopy, how it works and what it can provide in addition, before I finally summarize and then get to your questions. So atomic force microscopy is a technique where a sharp tip is raster scanned across a surface at a constant force. A number of feedback mechanisms exist for that. AFM is quite well established as a very high resolution method for imaging the surface of a sample down to nanoscale resolution, even down to atomic resolution. And this is really quite broadly applicable to many samples, including a lot of polymer samples, shown in one of the 3 examples here, C60 alkane basically imaged with molecular resolution. And AFM can go significantly beyond just imaging topography. That's illustrated in this slide on the left and right side with a number of images of a multi-layered polymer film. On the right side, we see tapping mode images. When we introduced tapping mode imaging about 20 years ago, it was noted quickly that the tapping phase images reflecting energy dissipation in the tip sample junction, that they really must have something to do with mechanical material properties. But really extracting real information out of those phase images has remained a bit elusive, and so it was very significant when very recently we introduced peak force tapping technology that allows us to have real-time material property channels, as shown on the left side of the slide here, where we have real-time adhesion and modulus channels. We can see that one of the 2 types of layers in this material has within the layer this adhesion variation, and how this is very pronounced modulus difference between the 2 types of layers that really wasn't reflected in the tapping mode phase image. And so AFM is actually, with this new peak force tapping technology and with peak force QNM, really a quantitative tool for mapping mechanical properties at high spatial resolution. And even more recently, we've seen that we can further extend this peak force tapping technology to other kinds of material properties, electrical properties. We can really extend conductivity mapping onto soft sample, onto polymers at the highest resolution without introducing artifacts damaging these soft samples. One example of that is shown here, where we see an image of a well-characterized organic photovoltaic, the well-known P.P3HT. The yellow color on this color map indicates locations of high conductivity that are seen to often coincide with very sharp protrusions, the more crystalline parts of the sample. And so with AFM really becoming a tool for not just nanoscale topography, but also quantitative mechanical and electrical characterization of soft samples of polymers, really the next very important parts of interest are characterizing these kind of samples thermally, thermal transitions, TGs, melting points, and of course also as part of that answering the question, what is the material under the tip, the chemistry? And with AFM as an ambient probe, conveniently doing that as a function of environment or of exposing the sample to different environments of processing, rare UV exposure, etc. Now, thermal properties, thermal transitions, characterizing those in bulk is something that's well established. This slide here shows a photo of an instrument for thermomechanical analysis, a technique where essentially a softening temperature is being determined very accurately and reproducibly, quantitatively, without any spatial resolution, just as a bulk value. It turns out the concept of thermomechanical analysis can indeed be transferred into the nanoscale. An important part there is having the appropriate probe. The probe is shown here. The schematic drawing on the top right of this slide shows how this probe is designed to be able to be heated by passing a current through it. At the same time, this is a sharp probe, a sharp AFM probe. The images at the bottom prove it, which are microphase separation images of a block copolymer, where the tapping phase image clearly shows the microphase separation. It's a 700 nanometer image. So,
welcome to GoToWebinar, web events made easy.
100 degrees Celsius in a controlled manner that really covers that wide temperature range that you want to interrogate polymer phase transitions. So really performing a nanoscale thermal analysis experiments, what does that mean? Typically, first an AFM image is acquired using the nano-TA probe. This image is then typically used to find target locations for individual spot measurements. So the probe is then parked at one of these locations of interest, and the temperature of the probe is being ramped up very rapidly. It's done usually significantly more rapidly than for bulk TMA, such as to keep the heating of the sample local. The deflection of the probe is of course being monitored. As the sample heats, it expands, pushes the probe up, deflection increases. That's that rising line in the graph on the right side, until the sample starts to soften and the probe starts to plunge down, at which point the probe is then withdrawn to avoid burying it in the sample. This nanoscale thermal analysis capability is available for our main research AFM platforms. In particular, it's available for large sample research systems, the dimension icon and edge shown on the top left and right of this slide, as well as for our small sample AFM systems, the multi-mode H shown on the bottom left and the ANOVA on the right. The Nanoscale thermal analysis solution consists of a hardware component shown in the center, as well as software probes and samples. In the following slides, I have a few individual examples of just performing these individual nanothermal analysis measurements, showing really the breadth of the applicability of this technique. Very often, if a sample is suitable for AFM, it's probably also suitable for nanothermal analysis. And this first example, looking at a polymer blend of polystyrene LDPE, thin film on silicon.
Welcome to GoToWebinar, web events made easy.
One component, the domain the other. Indeed, we can perform quite accurate measurements of transition temperatures and confirm that the matrix is polystyrene and the domains are low-density polyethylene. In this second example here, a very different kind of polymer sample, a multi-layer polymer sample, food packaging, literally a chips bag that was microtomed cross-section here. And the AFM image starts to provide information, reveals that layered structure. We can clearly locate different layers, and from the fine structure, and in this case the AFM amplitude image on the right side, we can immediately start to see that probably different materials are involved in the different layers, which may be suspected due to the different functions that this multi-layer packaging material needs to fulfill. Indeed, we can really confirm that with a nanothermal analysis where the blue lines correspond to the blue circles in the outside layers of the material and show a high transition temperature around 135, 140 degrees Celsius, corresponding to a choice of possibly high-density polyethylene, typical outside layer for such material. We see a much lower transition temperature in the center layer, the green circle and the green line, about 80 degrees Celsius transition temperature, consistent with a choice of, for example, ethylene vinyl alcohol as a chemical barrier layer. That would be a typical construction of such a multi-layer food packaging material. We also see this very rough boundary between these two main layers, possibly the presence of something else in between. They're very hard to tell from the AFM image alone. Looking at that red curve that was acquired at the location of the red circle in the AFM image, we see indeed yet a different, distinct transition temperature, evidence of a different material, an adhesion layer that keeps the two main layers together there. In this next example, yet again, a completely different sample, a toner particle that was embedded in epoxy in order to then be microtomed sectioned so that it can be investigated by AFM. And the AFM image on the right of the slide already suggests a core shell structure, and we performed a whole number of nano-TA measurements, and indeed the different softening temperatures confirm clearly a core shell structure for this complex toner particle. Indeed, nanothermal analysis can even find applications in the pharmaceutical areas where pharmaceutical applications have essentially material problems, such as, for example, in formulation, where mixing of different components as well as their polymers may have an effect on the efficiency of drug delivery, where, for example, in an amorphous formulation, it may be undesired for the material to crystallize and the API to aggregate. We see in this example where a nano-TA curve was recorded at two locations that we can clearly distinguish crystalline from amorphous polymorph. And lastly, in this section of individual nano-TA measurements, going back to a polymer blend in this case, here we're looking at a polyethylene oxide syntactic polypropylene blend, AFM image shown on the right side here. We seem to see a structure of a matrix with inclusions, with domains, and could again suspect that maybe the matrix is one component, maybe the domains the other one of this binary system. And indeed, taking a number of measurements, we see the transition temperature characteristic of polyethylene oxide in the domains and that of syntactic polypropylene in the matrix. Now, the previous image was a large AFM image. Zooming in a bit further, looking more at the fine structure, though, we notice more detail that we didn't notice at first. In the matrix, we see that typical fibrillar structure that you might expect for polypropylene, but also a lot of small droplets all over the matrix that already look a bit foreign to this sort of material. And indeed, taking measurements right on top of one of these droplets, we notice that we observe a nanothermal analysis curve that shows evidence of two transitions, that of polypropylene that's expected in the matrix, but also that of polyethylene oxide. So it seems we actually have smaller droplets of polyethylene oxide all over the matrix here. Now in these examples I've shown a lot of measurements of TG and melting point temperatures, and so the question is how meaningful those really are. Do they correlate with established catalog values for these kind of materials with results from, for example, TMA as one established method for determining these softening temperatures. So that investigation has been done, and the graph on the right side summarizes some of the results that show actually a very good correlation, where the slope in this graph is essentially 1.0. Offsets are on the order of a few degrees, and so that gives some indication of the reliability of this method and its correlation to bulk measurement. So in summary of this first part of the presentation, where we focused on individual nanothermal analysis, this analysis does provide phase transition temperatures, glass and melting transition temperatures with a sub-100 nanometer spatial resolution. So it provides for quantitative characterization and identification at the nanoscale in quite a broad area of polymers and their applications. Results correlate well with standard bulk TMA, really validating them. And the method is quite widely applicable with a wide temperature range that enables its use on most polymers. We've also seen in that last study actually that when we looked a little more closely and performed additional measurements, we uncovered additional detail on the sample. And so we were able to do that investigation there so far because already topography had given us a hint there. But of course, in general, it may be that there are additional variations that may not correlate with topography, which would then not be uncovered by a single or few single-point measurements, and of course be missed by bulk measurements. So actually, there may be additional detail here that we have missed. And really, since property variations and having a distribution of properties is intrinsic to polymers, this is a question that always arises. So really, while doing these individual measurements as a start, you generally want to do more. You want to do a lot of measurements. And so you want to accelerate and automate the measurements to enable that. And that's essentially what transition temperature microscopy provides. So within transition temperature microscopy, the individual measurements are nanothermal analysis measurements, as you saw in the previous section of the presentation. They are performed, though, very fast, fully automated with automated endpoint detection. So previous to these measurements, a whole array of measurement locations is defined, and then with a single click, the execution is started, and the system goes to a location, performs each measurement in a completely automated fashion, extracts the transition temperature, and immediately plots it in real time, generating a real-time transition temperature microscopy image directly showing the variations in transition temperature. This is a capability that is available on 2 of our AFM systems, the Dimension Icon large sample system as well as the Multimode 8 system. I have 3 applications examples to illustrate what this can reveal and how this can be applied. The first one is revisiting multi-layer films that have a degree of complexity because different layers are needed and have different functions and therefore different properties. And then there, of course, can also be additional complexity within a layer. In this first example, we'll walk through the experiment showing how it is performed with the new software that we have with this functionality now. So where first we are using an AFM image to guide the initial investigation, we're defining a few individual locations. Now we can execute any of these individual curves now automatically and very rapidly, and so far we're not seeing anything unexpected here. The software captures the data as well as the locations and saves that the complete information so we can later correlate the measurements to their spatial location. And we're then ready to go to a larger set of measurements to define a whole array of measurements and perform the transition temperature microscopy as is illustrated here for a modest-sized array On the right side again, the interface with the AFM image, the definition of the locations. On the left side then the result of the measurements, the transition temperature microscopy. So on the left side there in that color-coded map, we can immediately see that we have gone across two layers where we see that larger part of this map that has this orange color code corresponding to a higher transition temperature, the smaller part that's clearly greenish. But then we see a significant amount of variation beyond just this binary nature. And indeed, if we take this data and just plot it in a histogram, now with this large number of measurements, for one thing, we can very clearly determine centers of these two peaks, and so an average transition temperature for each of these layers. But we're also able to actually quantify a width for each of these transitions, a variation within each layer. In the second example, we're looking at a very different sample, a polymer sample where a solvent recrystallized surface has been generated. Modifying just the surfaces of polymer materials is quite common, and of course creates a surface layer that very locally may have different properties that would evade a bulk characterization. In this case here, we've exposed the surface to a gradient of solvent concentrations, something that may result in a not so trivial distribution of properties. And so here we see the result of this treatment. The brownish image in the background is the AFM image. Overlaid on it in the bluish color code, the transition temperature microscopy maps. And we see indeed a range of colors there, going from the bluish to the reddish as we go from right to left roughly. So from right to left, we have a tendency of increasing transition temperature as we have increased the solvent concentration going from right to left on the sample. And so there's a corresponding trend there, and something that we would not necessarily have predicted at all from the AFM image alone. We do see, though, clearly additional variation also in the transition temperature map. When we look at the overall statistics, also interestingly, we can see that we really do have a non-trivial distribution of properties here. We don't have one clear single transition temperature peak at all anymore, and so it really wouldn't have been very meaningful here just to do an individual measurement or just a bulk measurement on this particular sample if we really want to see how the transition temperatures vary locally. In this third example, we're looking at a pharmaceutical copolymer that is at the actual drug delivery vessel in its nascent state. So we're just looking at the surface as it is. We're looking for evidence of variations in copolymer blending, an important characteristic that has to do with the efficiency of delivering the drug, and something that is not necessarily obvious from other measurements. It really isn't, as we can see here on the left side, the AFM topography image. We see this is a rather rough surface with something like a 500 nanometer topography variation in this image. We see overlaid on that very rough surface this dense grid of very small indents that were produced by executing the transition temperature microscopy. You can see literally we have produced a grid here of hundreds of measurements, something that is really practical with transition temperature microscopy, as it is really being executed quite fast. And so then on the right side we see the transition temperature map that has been generated by this, and we do see some variation in transition temperatures, and some variation that really doesn't correspond to what we see on the left side. So for example, near the bottom left of this square array, we see this area where we see a lot of measurements with relatively high transition temperatures. We see these red pixels much more than anywhere else. Also, if we focus in on the top left quadrant of this transition temperature map, we see a lot of variations. See a lot of pixel variation from yellow to green to red. In contrast, if we focus in on the bottom right quadrant, we see a much more even distribution, a much narrower distribution of transition temperatures. if we again look back to the AFM image, it's just not something that we would have expected, that we could have already predicted from just that image. If we plot the histogram, the statistics, we see we can very accurately determine some average transition temperature, but there's also a very clearly measurable width to it, extended shoulders. We can clearly, from this, determine essentially the variation in the copolymer mixing, the property we were after. So in summary, you've seen that transition temperature microscopy really is a tool. It really brings nanoscale thermal analysis to the next level, where it can show a spatial variation in thermal properties. It's a means to execute a large number of nanoscale measurements rapidly. And it is a tool that complements Bruker's peak force QNM and peak force tunneling AFM. So the thermal analysis starts to become quantitative and complement the mechanical and nanoelectrical characterization. The spatial variation in thermal properties, it's important to note, is its own distinct property that may not correlate to other properties or may not correlate to topography. So it's truly a variation that may be missed by single nanothermal measurements, even when one attempts to target those two areas of interest. And executing a large number of measurements beyond just giving a spatial variation also gives more accurate determinations of an average quantity, but also really gives a more complete characterization of the complete statistical distribution of a property, something that's intrinsic to polymers and kind of information you really can't get in another way. And finally, complementing the nanomechanical and electrical characterization, overall this creates really with the dimension icon and the multi-mode 8, two very complete platforms for polymer characterization. So that's it. That's the end of the presentation. Thank you very much, everybody, for your attention. I'll now take a minute to have a quick look at your question, and in just a moment I'll start answering your questions.
Great. Thank you very much, Thomas. So I've organized these a little bit. It seems like that we have some instrumentation-based questions as well as some questions on the technique. So let's just get started. So first one is, what's the closest lateral resolution that you can expect to achieve with thermal mapping? For example, on polymers, when you do a second heat on a previously heated area, you may measure temperature due to changes in crystallinity.
Yeah, good question. Yeah, right. In general, if you do this in a well-controlled manner, you can keep the affected region to something like 100 nanometer diameter or smaller. So I'd say spatial resolution is sub 100 nanometers, and you wouldn't want to space measurements closer than that, or closer to previous measurements than that.
Okay. Measurement influence each other, and I'm assuming the thermal and the topographic measurement is the question.
Well, I mean, in principle, that's always a very important question for a scanning probe microscopy. There is always some limit where things where you hit some kind of limit, or things do start to affect each other. Of course, you can only look at samples with some degree of limited topography. Somewhere around 3 or 4 or 5 microns, you run out of height of your tip. If you're really not touching the bottom of your tip, you're starting to get artifacts. But that said, I would say there is relatively little influence of the topography on the thermal measurement, in that whether you're sitting flat on a sample or a little more angled, whether your contact area is very small or is a little bit larger, really doesn't affect the measured transition temperature that much. It'll affect a bit your spatial resolution, so that may vary a little bit point to point if the topography is extreme. But it has relatively little influence on the transition temperature map, I would say.
Okay, I have a number of questions sort of popping up here, which I'll bump to the front, all on the time it takes. So is TTM mapping time consuming, and then some more specifically, how long does each measurement take? How long would it take to do 400 measurements or a 50 micron scan? So can you just sort of generally comment on the speed?
Sure, yeah. It's a bit more time consuming than a regular AFM image, but it's not prohibitive to do a larger map. I feel that I did not push the limits with the examples that I showed there at all. Basically, I guess in conventional bulk TMA, you may have a relatively low ramp rate in your temperature to be as accurately as you can possibly be, and you may ramp at like a degree per minute or so. In nano-TA, you always keep it faster to keep the heating local, so it's not uncommon to ramp, say, 10 degrees per second. And as far as the instrument, the probe, the electronics are concerned, you could ramp at 10,000 degrees per second. And in practice, that's too fast, and at some point the data gets noisy. But ramping at, say, 10 to 100 degrees per second is not unusual. And so if you need to cover, say, 200 degrees, that means it takes you a second, 2 seconds to perform an individual point, maybe another a few seconds to cool down the probe. So it's a few seconds per measurement. So then it's a few minutes, or that times 2 for, say, 100 measurements. So for a small array, maybe it's 5-10 minutes. For a larger array, maybe it's 15-20 minutes. So it's a bit longer than a comparable AFM image, but it is actually, with a full automation and pushing nano-TA a little bit, it's actually feasible to do quite large arrays.
Okay, I think probably the next block of questions that we have are on how the temperature is measured, how accurate is it, and can you get absolute temperatures? So maybe we just start with how is the temperature actually measured?
Yeah, so that's a very good question. And in this nanothermal analysis, the temperature is not measured directly. This technique is very different from the scanning thermal analysis, which is a very different capability that's also part of this package. In nanothermal analysis, in scanning thermal microscopy, you have a probe that actually where you really measure the temperature of the probe. But here that's not done. Here this probe doesn't have any kind of thermocouple on it. The probe is calibrated on a known sample. So the whole accessory comes with a set of 3 known samples, and the probe is calibrated by basically measuring the transition temperatures on these 3 known samples. And so based on that calibration, the voltage ramp is then translated into a temperature ramp. And repeat measurements as well as correlation to the bulk measurements that you saw in the presentation show that this works quite well. So within a few degrees one can repeat measurements and can have accuracy maybe a few degrees. I think if temperatures are separated by, say, more than 10 degrees, you start to be able to distinguish them clearly. This is, I would say, it's not a technique where you can distinguish temperatures that are different by only a fraction of a degree.
What's the highest temperature that you can go to?
The probe can be controllably heated to about 400 degrees C. So you can look at transition temperatures approaching that. The probe can be heated briefly to much higher temperatures, 800,000 degrees Celsius. Can be flash heated to those temperatures to burn off contaminants if you do have contaminants stuck to the probe, but the controllable heating is to about 400 degrees C.
And sorry, go ahead.
To the previous question, do the measurements affect each other? I mean, one concern, of course, could be that the probe gets contaminated. In practice, though, when you control the experiment well, which actually the automation does very well, the probe doesn't usually get contaminated. So that's also another reason why you really can do large numbers of measurements. So it's not really usually in practice a big concern, but if it does get contaminated, you can flash heat it to burn off contaminant.
So maybe that's a good segue, and I guess it goes back a little bit to the first question, but a couple more questions have popped up on that. So one is each analysis can change the properties of the adjacent material. Is there a procedure for determining this effect, as referenced in Harding et al. In a 2007 paper? And then another question that, again, on the adjacent sites of very low and very high transition temperature, does this make sense from what's known about the tested sample? Is it possible that adjacent measurements cause problems?
Yeah, certainly. I mean, there is a limit to how much one can localize the effect, which depends a little, of course, on also the thermal conductivity of the sample and on how fast you ramp. One can certainly study that by making measurements at various distances to a previous measurement, and one can certainly do such things as varying the ramp rate, and the ramp rate actually really can be varied over many orders of magnitude as far as the instrumental capability. And so in that sense, there are means to sort of do control experiments and do those kind of studies to see if there has been a modification of the sample where maybe in some cases where you're really concerned with distinguishing essentially two different chemistries, it may be a very simple question. You may have very clear expectations of what you do, what you don't do to a sample. If it's what I showed in one of the pharmaceutical examples, where it's about a polymorph where one may actually be transformed into the other through the heating, then of course it's more subtle what the effect of a measurement may be.
Okay, I'd say now there's probably a fairly good group of questions on just compatibility and options. So does this work on the Bioscope Catalyst?
We don't have it as an option right now on the Bioscope Catalyst.
Is TTM compatible with QNM or Tuna?
It's a question of sort of what cantilever is needed for the techniques. The transition temperature microscopy, just like in general, the nanothermal analysis does require its own special cantilever. Let's say QNM, if you use peak force QNM in a qualitative sense, it's quite flexible as to what probes it uses, and there are two different spring constants available on the nano-TA cantilever. So in general, with QNM, you can certainly use the same cantilever. So whether you do it in one run or in two runs, it's very easy to interrogate the same area with these two techniques. Now, when it comes to conductive or tunneling AFM, you do need a conductive probe, and so you need a different probe. So there you need to really sort of introduce a means for you to find the same location after you change probes.
So following up on that QNM question, or quantitative nanomechanics to define the outcome, the examples shown appear to be similar to those which QNM should be capable of sorting out, chemical makeup of the surface, but DMM is significantly lower. Exactly what type of system would TMM and scanning thermal be better at than QNM in terms of being able to resolve?
Well, I mean, right. There may be many cases where ultimately you do get the same answer with both. It depends, I guess, if you're interested in one versus the other property as a property, or if you use the property as a proxy for chemistry. It depends on which property does that very well. You know, maybe you have some samples where from one chemistry to the next, the transition temperatures are very different, but mechanically the stiffness is very similar, or vice versa. You know, the opposite could be the case. So if you use them as a proxy for chemistry, it could go either way. QNM certainly does have higher spatial resolution and damages the sample less. I mean, with QNM really you go down to 1 nanometer or so to your full topography resolution essentially. The thermal property mapping is lower spatial resolution. But it depends on the sample. I think it's absolutely true that both can actually be applied, and so that's potentially a great strength that if you are in a situation where you want a very complete picture and the highest possible confidence about what's what on a sample, then it's the combination that's very powerful.
Okay, so back to the compatibility. Can we use this technique on metallic samples?
Probably metallic samples usually are associated with very high thermal conductivity, I guess. I don't know if that's universally true of metals, but just offhand thinking of it. You know, one problem for the technique would be a very high thermal conductivity, because that makes it very hard to heat locally. So I think probably not. It's probably it's quite suitable quite widely in polymers, probably not so much for metals. Yeah.
Could this be combined with atmospheric control?
Yes, essentially no problem. The technique has no problem with atmospheric control, and also as far as our accessories, whether it's our heater cooler chambers, especially thinking of, say, the atmospheric cooler on the multimode, no problem, or thinking of, if we're thinking of the heater cooler though, well, we are using a special probe holder here though, so when I say heater cooler chambers, maybe not, but the atmospheric hood on the multimode, no problem, or our glove box, 1 ppm environmental control, no problem also.
Okay. So I'd like to move back to, I guess maybe a little bit on calibration. A lot of questions have come up on that. Is it, in particular on absolute temperatures, so the question is it also possible to measure absolute temperatures, for example, measuring the temperature distribution on a chip?
Oh, yeah, no. No. What the technique does is it measures when a sample gets soft, right? So the probe temperature is being ramped up, and you notice when the deflection suddenly drops. So you could put the probe on a chip and measure when something melts on it, but maybe on a chip there isn't anything that would melt in that temperature range. Well, unless there's some polymer somewhere. So, but no. So the temperature distribution on a chip, there is a technique to measure that scanning thermal microscopy. It also uses a special kind of probe. It's also a capability that is included with the Nanothermal Analysis package, but it's a different technique. It's a technique that uses a probe that has a resistor, a thermocouple, built across the very tip of the probe. That makes the probe a very sensitive measurement device for local temperature variation. It also makes this probe quite sensitive, though those probes cannot be heated to hundreds of degrees, and they're much more sensitive than the nano-TA probes. With that completely different technique that has really little to do with this and nothing to do with TTM, with this different technique, STHM, one can indeed map out variations of thermal conductivity and variations of temperature, and one can easily within an image decide where there is a higher, where there is a lower temperature. It is not necessarily trivial though to make absolute statements of temperature there, as those measurements do depend on tip surface contact area quite a bit, definitely more than nano-TA measurements. So absolute temperatures, I'm not so sure, but temperature variations, in principle, there is a technique STHM for that, yes.
So there was a follow-on to that STHM question. What resolution is that capable of?
STHM is capable of detecting temperature variations down to a fraction of a degree, I would say, maybe 0.1 degree. As far as temperature resolution, spatial resolution, tip end radius on those probes is better than 100 nanometers. I'd have to look up at maybe better than 50 nanometers. Not quite as sharp as a normal AFM probe, but comes close.
Okay. Back to the absolute temperature theme. How can such techniques give absolute temperatures if the pressure exerted on the sample depends, among other things, on tip geometry? I think you may have answered that a bit, but if you want to comment again.
Yeah. So I mean, there are a number of reasons why the measurement is sort of an approximation and has in principle some faults in it, but in practice it turns out the correlation with bulk measurements is really quite good. In practice you're within a few degrees, even though yes, the tip geometry should play a role, and one might argue that as the sample expands, the force isn't exactly constant. One really does find that empirically it's not a big factor. So at least to the accuracy, the repeatability that I showed here of a few degrees, it just isn't a problem. Also, if one is concerned about a variation from probe to probe, since each probe individually is calibrated anyway, some of that effect is then removed.
Okay, along the same line, how do you know the exact temperature at the probe tip contact point?
Well, in a sense, that's the only temperature you know, because that's the temperature, because you calibrated the probe on a known sample, right? And so you melted a known sample at the temperature, at whatever temperature it melted. So you knew at what heating voltage you generated the temperature under the probe that melted that sample. What you don't know is actually what the temperature of the probe is, say, on top of the probe where the heating element is. But you do know where it matters because you just empirically calibrated it.
Okay. So I think, yeah, calibration seems to be an issue coming back in. More questions on that. How often do you calibrate the probe, and is the correlation linear across the different samples?
When you get a quadratic calibration curve with heating voltage, and that's quite accurate. You typically calibrate a given probe once, unless you don't expect the probe through use to vary a lot unless it got contaminated, where then maybe you get the same curve several times in different areas and different samples, or you have other evidence of that. But unless the probe got damaged in that manner, for a given probe, the calibration doesn't really change. But it is relatively straightforward with the given set of calibration samples, say, to repeat a calibration after the measurement just to confirm.
Okay, so now there's a number of fairly specific questions. So the Dow data showed independence of heating rate, but classic viscoelastic measurements analyze variable temperatures and rate dependencies to extract more fundamental information such as activation energies and WLF versus Arenas response. Have you had any luck in doing such things, or has your user base reported any such studies?
Not to my knowledge, with nano-TA, I don't think it would be I don't think it would be a very big strength of nano-TA to do that, but I may not know everything there. There may be more studies out there than I'm aware of right now. I mean, I think nano-TA can give you fairly accurate temperatures, but clearly with an extremely slow bulk measurement, there are some things you can do better. Since to keep the effect local, you have to go fast. I mean, that will limit some aspects of your measurement. So I think you have some limitations in doing this heating rate measurement for real practical considerations that are hard to get around. But there may be more studies out there than what I know right now.
Is it possible to determine with peak force tuna the difference in terms of surface energy on the surface before and after corona treated? So I guess the question is on surface energy.
Surface energy. No, I don't know right now how surface energy would relate to conductivity. I mean, with peak force tunneling AFM, we're really making a DC current measurement. If surface energy, in some sense, is related to related to a DC conductivity in a 2-point measurement, then in principle, yes. But I don't know that.
Couple questions on application, maybe combined with resolution. Is it possible to determine the difference temperature TM in a section of catalyst in different crystal domains?
Sorry. Could you just repeat once more?
Yeah, maybe it's not completely clear. Is it possible to determine the difference temperature in a section of catalyst in different crystalline domains? So I think the question is, can you get the transition temperature within at different points within a single domain?
Yeah, I guess depends on how large the domains are. I'd say, I mean, do you have the your typical spatial resolution on the order of 100 nanometers or a little better? If your domains are large enough, then in principle, yes.
A couple questions here on the three-dimensional aspects. A lot of focus on surface analysis, but how deep is the probe going? Of course, be modified to go deeper into the sample and then compare the two results and extract information.
Yeah, certainly. One can vary how deep one goes in. I mean, maybe the most common is to, and in practice, is to withdraw the probe relatively to work with a modest force in the beginning to begin with, and extract the probe relatively quickly after the softening occurs. But and then so that one can have a look at the indents that one leaves at the plastic deformation one leaves in the sample afterwards to estimate the probe depth. And so it may be comparable to the characteristic size of the melted of the damaged area, maybe on the order of 100 nanometers or less. But one can certainly vary that by simply letting the sample soften a little bit longer before retracting the probe. Yes.
Okay. Maybe back to resolution with particles in the 50 to 100 nanometer range. The transition temperature be measured.
It may be challenging to do that accurately and not be affected by the substrate below them. That maybe the sort of size range becomes very challenging.
Okay. How does the substrate underneath the material affect the analysis of the surface crystal structure? Or maybe another way, what's the minimum that you can conduct this type of
What's the minimum thickness, or?
If you have a thin film, what's the minimum thickness before the substrates?
It depends a bit on the sample, in that it depends in principle on the thermal conductivity. But I think at 100 nanometers it may become rather challenging. At several hundred nanometers, it's not a problem.
Okay. How good is the comparison with DSC in terms of glass transition temperature? Has that been, are you aware of that correlation been examined?
I don't know if it's been examined with respect to DSC. I guess, yeah, the one I showed was a correlation with TMA.
Okay. Let's see. I think there are a number of other questions here and some comments too, but I think that some of them we'll probably answer offline as we're approaching the end of the session. So I'd like to thank our speaker, Thomas Mueller, and thank all of you for attending this webinar today. Please, again, don't forget to fill out the exit survey on the way out, and it does help us make better webinars in the future. So thank you very much again.